Okay. Yeah, let's make a start. Yesterday, we introduced a quite crucial observable, or quantity, better to say, we have in cosmology, which is the co-moving sound horizon. So the sound horizon intuitively is a characteristic length scale you have in the primordial fluid, and it corresponds to the distance a wave can have traveled by the time of recombination. And to get an idea of what the sound horizon is, we looked at a simple toy model yesterday where we just have radiation, so equation of state 1/3, a constant sound speed, and then the sound horizon is indeed just the sound speed times the time that has elapsed. You can define some initial time, which is the time at which these perturbations have been sourced initially until some later time eta. And in that case, everything is simple, but you can rewrite this expression in a slightly artificially looking way. You can write, so first of all, you can neglect the initial time. So the initial time is proportional to the inverse conformal Hubble parameter, which at early times in the universe is negligibly small, so we can drop that. And then we rewrite eta as an eta integral, and then we do this usual trick where we rewrite the conformal time integration in terms of a redshift integration. And we end up integrating from some redshift z corresponding to the time eta to infinity, the sound horizon over the Hubble parameter. And so that way we can relate the sound horizon to a particular cosmology which determines the expansion history. And then in the case of the CMB, things are a little bit more complicated because you have a coupled fluid between photons and baryons being non-relativistic. This leads to a time-dependent sound speed. So the CMB sound horizon is the direct generalization of this expression where you replace the constant sound horizon by the z-dependent sound horizon. And here you integrate from decoupling, redshift of decoupling, up to infinity. So this is an important quantity, and we have seen yesterday that it's different determinations of the Hubble parameter today are very sensitive to the value of the sound horizon. So in particular, the CMB measurement determines the angular scale of the sound horizon in the CMB, whereas the BAO measurement determines the angular scale of the sound horizon, or almost that quantity in the matter power spectrum. Okay, this is the recap. And what I want to do today is to start the second part of the lecture, which is beyond lambda CDM. So this is the point where we enter new territory, so to say. And well, the first aspect here is we are going to talk about new physics, but the idea of this part of the lecture is to focus on general mechanisms, not so much on particular models. That's going to come in the last part, but on very useful mechanisms in cosmology to think about new physics and to parameterize it. So the idea is that you kind of get a toolkit to work with cosmology, go beyond lambda CDM and try out your own ideas and test them. Okay, new physics, but the question is, of course, how and when. So there is one key observation we made already yesterday in the discussion. So when we measure the sound horizon, we don't measure that scale directly, we measure the angle under which we see it. So the picture is always the following. There is the sound horizon scale, and what we measure is this angle under which we see it in the sky, so to speak, and this is of course related by the co-moving distance to the surface of last scattering in the case of the CMB measurement, or the distance to the redshift of a particular survey we use to infer the BAOs. Okay, and here already at this level, there is an important observation. This distance is dependent on late universe physics. And by late, I always mean after recombination, and by early, I always mean before recombination, coupling for that purpose. And the sound horizon is early universe physics. So the CMB measurement brings early and late universe physics together in a very particular way. And as we have seen yesterday, this angle, of course, is the ratio. So this is now the ratio of co-moving scales. Yesterday we phrased it as a ratio of physical scales. So then you would multiply both by a factor of A, and then you recover this angular diameter distance we talked about yesterday. So just to not confuse you, I mean, people also often call the co-moving distance the angular diameter scale, but that's the co-moving angular diameter scale. So one always has to be a little bit careful what is used. Is it the physical or the co-moving one? Okay, in any case, so now the question is, we want to raise H naught, right? This is the co-moving distance from us to the surface of last scattering. And this is also called the co-moving angular diameter distance, because yesterday we have defined the angular diameter distance as A times chi. So if that is the physical, if that is the physical angular diameter scale, then of course that is the co-moving one, because there sits a factor of A. That's just a convention of how people call these things, just to, yeah. So, but for us, this is the co-moving scale, and we divide it by another co-moving scale. So there is no problem there. Okay, so now, let's think about what happens if we raise H naught within lambda CDM. And we have seen yesterday how this co-moving distance depends on H. It depends inversely on H naught. So the co-moving distance is going to go down. And if the sound horizon is fixed, I mean, as I said, it's early universe physics, then the peak in the CMB, I mean, the angle goes up, and the peak is going to move to the left in the CMB. Of course, we don't want that. So in the case of the CMB, there are two obvious remedies to that. So one possibility in the CMB is to lower the sound horizon. So if we want to increase H naught, we can lower the sound horizon and leave that ratio invariant, obviously. But there is another possibility in the case of the CMB. We can also change the expansion history at late times. for Z smaller Z decoupling such that the co-moving angular diameter distance, or to the surface of last scattering, is invariant. So if you look at that expression, then we have seen that raising H naught sits inside this parameterization of the Hubble parameter, kind of brings it down, but then you could change the energy budget at late times to compensate for that and make this invariant. So you have in principle these two possibilities to raise H naught without moving the peaks, which is unacceptable.
The sky of Z decreases, theta also decreases.
Oh, sorry. Yeah, that's important. Okay. Yeah. So that's the idea. I mean, the increasing H naught, if you don't do anything else, brings chi down, and then either you modify whatever else the chi depends on, or you lower the sound horizon. These are the two possibilities for the CMB. But the BAO turns out to be more constraining. Here, in that case, raising H naught requires lowering RS in order to keep it invariant. And the reason is that in the case of BAO, at least the ones at low redshift, then you can expand this expression, and what you find is that they don't have any, here you just don't have any freedom to play with additionally. So there is little flexibility here. And so what you see if you look at that ratio is that you constrain H naught times RS, which has to be approximately constant. And as I said yesterday, this statement is a 1 to 2% statement. Okay, so what from this we learn that the obvious way to address the Hubble tension and be compatible with BAO and CMB measurements is then to lower the sound horizon. And what you find is if you want to bring the Hubble parameter up by 5 to 10%, you also need to lower the sound horizon by 5 to 10%. So the strategy we are going to follow in the rest of this lecture is to find new physics that achieves that. Yeah. 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 So in the case of the BAO, the measurement is taken at a much smaller redshift, a redshift of order 1, which gives you less, simply speaking, less flexibility to introduce drastic new physics around that time. I mean, the detailed argument, you have to be a little bit more careful because you could have very singular features at that redshift that compensate for something, but then there are also the supernova measurements which constrain the shape of the expansion history. So that's what I mean by little flexibility. So let's put here together with supernova. The shape of the low set expansion history is very much constrained, and that gives you little flexibility to play with that. So I'm not saying this is an absolute no-go theorem. I'm just saying the obvious path forward for me is to lower the sound horizon, because then you don't have to, you don't run into these problems with BAO and supernova measurements you would otherwise have. That's the statement here. Yeah, so there's this, that's the case that can be made for early universe modifications of lambda CDM. That doesn't mean that the late universe might not also change due to these modifications, but it's more like a necessary rather than sufficient requirement, I would say. Okay, so the strategy is find new physics that lowers the sound horizon and as a consequence raises H0 as we need to do that to compensate, to keep the angular size fixed. But the exciting thing, and this is also what got me into this whole kind of field of modifying lambda CDM and so on, is the observation that the sound horizon actually is a quite constraining quantity. And what do I mean by it? So if you look at the at this expression, so you take the integral from Z decoupling to some UV cutoff, and you integrate the sound horizon, I mean the sound speed divided by Hubble. Then if we send ZUV to infinity, this is exactly the sound horizon, right? But now we ask, where does this integral pick up 90% of its value, say, or 95? I mean, let's say 95. So in other words, I want to know what this quantity, the sound horizon, is really sensitive to in terms of redshift. And what you, so because you see, I mean, the earlier, as we go to earlier times, Hubble becomes bigger and bigger, and that shuts off the integrand. So we are not going to pick up much value for the sound horizon at very early time. It all happens fairly close to recombination. So if you do that calculation and infer the value of ZUV, you are going to find that this is, and you're going to do that exercise, it's a redshift of around 25,000. So this means that in order to change the sound horizon by 5 to 10%, without doing anything increasingly singular at very early times, we need to introduce new physics in a narrow redshift window between decoupling and that redshift. And that's exciting because that's really just the EV scale in terms of energy scale. So if you look at the energy budget in that epoch, it's going to be of that order. So we are talking about low energy physics, so introducing new physics at the EV scale. And that's interesting and exciting because this physics falls entirely within the CMB epoch. So modes we observe in the CMB, or all modes that enter during this interval we observe in the CMB. So it's a very constraining setting. So no matter what we do, if we get it wrong, CMB is going to tell us. And that's an ideal situation when we talk about new physics. We want things to be maximally constraining. Otherwise, we have too much freedom to play around. We want a situation where data can tell us if what we are doing makes sense or doesn't make sense. So that's why I personally got excited about these early time modifications. Yeah. Mm.
So the frameworks that are entering during that time, so they will create some large-scale structures or some structures.
Mm.
So we must have some bound on those new physics from the galaxy surveys or...
Yeah, galaxy surveys and CMB physics. If the thing is, if you introduce new physics way earlier, say at a redshift before BBN, I don't know, redshift of 10 to the 12, say, then all modes we observe are still outside the horizon and happily frozen. They don't care about that new physics you introduce. So this is the exciting aspect of going along that path. Okay, so what is the method of exploiting that kind of possibility? So for that, yeah, I mean, it's a very crucial quantity, so I think I write it down now for the third time today, but it doesn't matter. So there are three ways we can shrink the sound horizon, and we are going to make use of one possibility, but let me first talk about the other obvious ones. One is to change the sound speed. So if the sound speed is smaller than what you have in lambda CDM, it would lower the sound horizon. And I think in principle that's a possibility. You could play with the physics of the photon baryon fluid, but I've never seen anyone kind of successfully exploit that possibility. But maybe there's a possibility, I don't know. And the other more popular possibility is to change the time of decoupling. That of course requires you, that fits very nicely actually with the first lecture today where you have talked about recombination and the physics of recombination. So this requires changing the physics of recombination. So there are different possibilities of doing that. So I discuss in these notes, I put online a few popular ones and put papers there. I'm not going to discuss it here. But one way of doing it is to change Thomson scattering. Of course, everything crucially depends on interaction rates during recombination. So how can people change Thomson scattering without spoiling the observations we make now in collider experiments and so on? And the idea is to make the electron mass time dependent. So they look at models where the electron mass was different in the early universe compared to today, and then you find that this affects Thomson scattering, which is inversely proportional to the electron mass, or the square of the electron mass. And this is how you can think about new physics that changes the time of decoupling, and that's an interesting possibility, I think, in itself, but also not so easy to achieve, because changing the electron mass is not easy, because you do it in the visible sector. It's a highly constrained physics from different directions. So doing that in a consistent field theoretic way is, I think, not easy. Instead, what I'm going to do here is to change the expansion history via an energy injection. So you can immediately see why an energy injection helps, because an energy injection, Hubble is proportional to the root of the energy density. So an energy injection is going to increase Hubble and bring down the sound horizon. So that's the path we are going to look at. So let's start there. So the idea is to to take the lambda CDM expansion history, lambda CDM, and add some new energy component I call rho x. And the requirements on rho x are going to be that it is sizable in this redshift window. So there is a set between 25K and recombination where omega x makes up at least 0.1% of the energy budget. That is what you find you need to lower the sound horizon enough. You're going to do an exercise a little bit along those lines. So you need a sizable energy injection. And then, but at the same time, we don't want this new energy density to overwhelm the budget. We still want to have a notion that we are close to lambda CDM. We want to look at a small, still smallish deviation from lambda CDM, especially at late times. So that means initially at least, we look at modifications that are only operative at early times. I mean, this can be dropped in principle. I mean, it's more like a simplifying assumption. And then, most importantly, there are certain phenomenological constraints, obvious constraints. Of course, we want to fit the CMB and in its entirety. But before thinking about that, we need to set things up in a way such that the angular scale of the sound horizon in the CMB, and so which is a very precise quantity. So the error is smaller than 0.04%, and H0 times RS being constant, which we get from CMB. So that constant is predicted at 1 to 2% level, that these quantities are fixed. So we want to introduce that change in such a way that this holds. And by only looking at these requirements, we can already find certain, as I call them, secondary effects. So the primary effect of such a modification is, of course, to increase the Hubble parameter. That you see directly from here. We are going to lower RS, and the only way to satisfy that, we need to increase H0. That's what we want. That's the primary effect. But there are going to be secondary effects we need to worry about, because doing something as drastic as that is also going to change other quantities and might interfere with our observations. So, yeah, and the first of these secondary effects is a change in omega matter, the dimensionless absolute matter density. So it's little h squared times omega m, where I remind you that little h is defined via this relation. So it's the dimensionless Hubble parameter. Okay. And to understand what's happening in that case, let's write. Okay, let me put that. Maybe, yeah. Okay, let's put it here, anyways. So we look at the angular size of the CMB. Now we know it's the sound horizon divided by the co-moving distance to decoupling, and that we can write as RS, and we can write out this distance. But now I do it in a way where I already introduce omega. So it's an integral from zeros to decoupling, and it's 1 divided by omega m. We have seen some that integral already yesterday, plus h squared minus omega m. And here I have dropped radiation. I could have included it. It wouldn't have changed the argument, but the point is that this integral gets its main contribution from low redshift, where we can neglect the radiation part. So this is, sorry, it's to the power 3. So there's a typo in the notes in any case, yeah. And this is just parameterizing the expansion history, and we need to keep that quantity here, which doesn't depend on H. So now what we can do is we can use this relation to eliminate H naught. So instead of, let's do that. Use this relation to eliminate it in terms of C naught. But let me introduce a C naught tilde, which is the little h times Rs. So if I do that, what I get is that the integral from 0 to decoupling dz. So I just use it to get rid of h here and have everything expressed in terms of the sound horizon. So it's omega m 1 plus z to the power 3. Let me see. Yes, minus 1 Rs squared plus C naught tilde squared. Okay. And all of that is to the power minus 1. And this has to be fixed. So let me see, did I do it right? This brings us to C naught squared, but then I've also taken down this Rs inside. Yeah, this is how this showed up. So the Rs dependence in So you should be able to easily get from here to here by just substituting H with that and taking Rs downstairs, and this is just the inverse of the whole expression. But the point, of course, is that all of that needs to remain fixed. So what we are now doing is we lower the sound horizon. We have already taken care of the BAO constraint, but we want to do it in a way such that theta is fixed. But this can only be achieved by changing one of the other quantities this depends on. But the only other quantity it depends on is omega matter. So what we already see, in order to satisfy these two simple constraints, we need to change the matter content of the universe. There is no way around that conclusion. And what you find is that that omega m times Rs squared has to be roughly constant. That's the condition you need to satisfy in order to satisfy that condition. So that you see, because this integral picks up its main value at low redshift. Well, you just see it from this. It's degenerate in omega m times Rs squared. So if you keep that constant, this integral is not going to change its value. And from this, we see that the change in omega m, because here it's omega m times Rs squared. So this relation is quadratically sensitive to the sound horizon. So we are going to see that delta omega divided by omega m is minus 2 times delta, the change in the sound horizon, divided by Rs, because it has this quadratic dependence. So this means that omega m is particularly sensitive to change in the sound horizon. So we will increase it by 10 to 20% if we decrease the sound horizon by 5 to 10%, because there is a minus sign in this factor of 2. So this is potentially bad news, because you change suddenly the matter content of the universe by 10 to 20%, and that has immediate consequences, because if you look at the gravitational potential, we talked about it yesterday, and let's look at the combination phi plus psi as a function of time. Then what happens if you increase omega m? So I told you yesterday that the gravitational potential is on superhorizon scales is just frozen out, it's constant, but then at some point it enters the horizon. And it enters it, we are looking at modes that enter the horizon during radiation domination. So then we have seen phi decayed. I mean, that was the statement that radiative pressure acts against collapse. So the gravitational potential decays. But then at some point there's equality. So matter domination sets in. And we have seen that during matter domination, the gravitational potential for all K modes is constant. That was that solution we have seen by looking at this closed form equation for phi yesterday. So this goes to a constant. Now what happens if we increase omega m? This means that matter domination sets in earlier. So we move the time of equality to earlier times. This means that the same mode enters the horizon, starts decaying, but becomes a constant earlier on. So in other words, you have changed the strength of the gravitational potential at late times. And as you will learn in the CMB lecture, I mean, this change in the gravitational potential is quite important for the CMB phenomenology. So it's the integrated Sachs-Wolf effect, which is most sensitive to these decays, because photons that travel towards us, they feel that slope. And the CMB is going to depend on that. So we are going to get problems with that. And we are going to get problems with, with the fact that gravitational potentials are overall stronger at late times, which enhances structure formation. I mean, stronger gravitational potential just lead to more clumping. So this is a potential problem. So no matter what we are going to do in terms of new physics, we need some compensating mechanism to account for that increase in omega m. And we will see that these modifications I'm going to suggest, they have a mechanism which counteracts that and which shifts matter domination back again effectively. Yeah. 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 But this is exactly, I mean, so this is exactly why I have eliminated all H dependence from that equation, because otherwise it gets very confusing, because of course capital omega, if you increase H, it goes down, but this is really the physical, I mean, it's not divided by H naught squared. So this whole expression doesn't depend on H naught anymore, and for that reason, there's no, we can simply read off what's happening, because right now we had in mind to lower the sound horizon, but this tells us if you do that, well, you are going to need to increase little omega matter. Yeah. Of course, capital omega matter, whether it increases or decreases, depends a little bit on how much Hubble compared to little omega increases. Yeah. Okay, very good. This was the first secondary effect. We need to keep it in mind for the models I'm going to discuss. And then there is another secondary effect, and that is a change in in diffusion damping. So that is an important CMB effect, and you have all seen the CMB power spectrum at some point, I guess, and you are going to see it at least in the lectures that follow. So then you know that there is a damping tail. So at large L, the CMB is damped. And what you can now see is that this damping behavior is changed once you decrease the sound horizon. And the way to see it is, okay, here, because I don't have time to derive the CMB damping in detail, but so the damping behavior, the CMB power spectrum falls off as an exponential for a given K mode. It can be written as some damping scale, RD, times K divided by 2 pi squared. So this is the behavior of this damping. You have to convert it into L's to see it in this picture. And this damping scale depends mainly on the free mean path of photons in the photon baryon fluid. And so we can write down what it is. The damping scale squared is the integral from decoupling to infinity of dz some function which is roughly the mean free path of photons divided by h of z. And the fact that there is a square here has to do with the nature of the process. So what happens is that photons in hot regions diffuse into colder regions within the plasma, and that is a random walk. And in case of a random walk, the distance you travel grows with the number of steps you take, the square root of the number of steps you take. And this leads to this square here. Okay. And so now what you need to, so very qualitatively, what you see is that if you compare this with the sound horizon integral, which is this, so on one side we are going to increase h to bring down the sound horizon. Well, but then we are also going to change the damping scale because, well, if we increase h here, we are going to increase it here too. So there is this quite unavoidable conclusion that by having an energy injection, you're going to change the damping properties. So now I have a derivation in my notes. I think I will skip the details and you can, it's a simple, yeah, sorry. FD, yeah. This is also a function which has a slight Z dependence. You can think of it as the mean free path of photons. So it's roughly the mean free path of photons in the fluid. It's a little bit more complicated when you work out the details. But yeah, you can understand that it should depend on the mean free path of photons because this is really a diffusion process. So which is controlled by how much scattering you have in your plasma. Okay. Mm-hmm. Yeah, you could think about compensating for that, but changing kind of the delicate physics of the photon baryon fluid. Maybe you could come up with something, but I doubt it because you need a relatively drastic change in H, and that change is going to be quite localized in redshift. So normally this doesn't vary a lot in a small redshift window. So having this compensate for that means this also has to be something quite drastic in a small redshift window. So it's not obvious how to achieve that. So what you can do is you can look at a generic modification of the expansion history, and then you can do a variational problem. So you can ask, well, how does the sound horizon change under that? And you are going to find that the sound horizon changes as such, h squared times the change in Hubble, and you can do the same for the damping scale, and you are going to get that it's minus a half because the damping scale comes with the square here importantly, and then you get, of course, just divided by h squared times delta h, so very similar expression. And okay, I'm not working out the details now, but it's easy to show, and it's in the notes in more detail. From this, you learn that, yeah, if you make the assumption that in the region where this delta H peaks, the sound horizon and this mean free path of the photons is roughly constant. So if you assume these to be approximately constant, then you can derive the following relation, that the ratio of the damping scale divided by the sound horizon, the change of that under this change, is going to be minus a half RD divided by the sound horizon times delta RS divided by RS. So let's look at that equation. So this tells us that if we lower the sound horizon, so delta RS is negative, since we have a negative sign here, we are going to increase the ratio between the damping scale and the sound horizon scale. So why is that an interesting ratio for us? Well, I can show you. Because what I wrote down here is just the fall off in K space, but we have to convert to L space, and to do that we need to use that L. For large L is just given by K times the co-moving distance to the surface of last scattering. Then we can replace K in this formula with L. But that will bring us a dependence on this distance scale. So then we can also use that our theta s is the sound horizon divided by that distance scale to also eliminate that distance scale. And what we are going to find is that the CLs at large L are going to be proportional to the exponent of minus 2 times RD divided by RS times by theta s divided by 2 pi L and everything squared. Okay, so this is just using these two relations inside here, and then you find that the damping tail as a function of L looks like this. Sorry. And what is important is that, again, we know this is fixed. There is no freedom in this quantity. This is fixed. So truly the damping is controlled by the ratio of RD divided by the sound horizon. And now we have just seen that this ratio goes up as we lower the sound horizon, because here's a minus sign. It goes up. So in other words, there's more damping. If RD over RS goes up, there's more damping. And so we get enhanced damping. So again, there is a secondary effect. We get enhanced damping. this is not tolerable. We measure the CMB, we measure its damping, so we need to have a compensating effect. And in this case, I can immediately tell you what the compensating effect is. So if you look at how the CLs depend on the primordial power spectrum, so this, you're going to learn more about this tomorrow, I think. This is the transfer function, which takes the initial conditions all the way until today and relates it to the CLs. But this is convoluted via this momentum integration with the primordial spectrum. You probably have seen in the inflation lecture, and that can be written as the primordial amplitude times some k divided by a reference scale ns minus 1. So this is the primordial spectrum of perturbations. These are our initial conditions from inflation, and they are convoluted with some transfer function. That transfer function is a complicated thing because it contains all the information about the dynamics in the fluid. So you need to solve all these fluid and Boltzmann equations to derive it. This is really what all these the class code is doing, and it gives you the CLs. So now we have seen that we suppress the CLs at large K, and what you can see is that you can approximately compensate it by increasing NS and AS. That's what you're going to see in these models, that once you have an energy injection, you are going to change your prediction for NS and the amplitude and tilt of the primordial power spectrum. So this is, of course, a qualitative argument, because this is also not a perfect cancellation. This is a power law, and this is an exponential fall-off. So it's not going to be perfect, but that's in a way what you want. You want to have signatures in once you introduce a new model, and you hope, of course, that these deviations from what you had before give a better fit at the end. But of course, the overall fit should be very similar to lambda CDM. So this is what you are going to see. You are going to see a partial compensation by NS and AS going up. And this is an important reminder that when we look, you might have seen this plot about inflationary model building, where you look at the lambda CDM constraints on the tensor scalar ratio over the spectral tilt. And that, of course, depends on lambda CDM. But now, once you change lambda CDM, these conclusions about the very early universe also change. And this is sometimes something which I think is not emphasized enough, that these plots very much depend on our cosmological model. And since we learn in a very indirect way about these quantities, they are also sensitive to what happens at later times. Okay, so this is what I wanted to say about these things. Yeah. Yeah. Yeah, yeah. Yeah. Because if they increase, then for large K, you get more power. And here you have the problem that for large L, which means large K, you have too little power, right? So that's how the compensation works. But of course, you cannot compensate it perfectly. You cannot compensate an exponential fall-off with a power law correction. But yeah, it turns out that within the observable range and so on, you can still get a well enough compensation such that the overall fit to the CMB, at least for the most successful models within this realm, is not made any worse. To the contrary, it can even improve a little bit, depending on the model. Okay, so this has implications for inflation. I don't want to overemphasize this point. I mean, of course, now we are saying we want to resolve the Hubble tension, and by doing that in a particular way with early universe physics, we are changing predictions about inflation. But this is just an interesting observation at this point. Okay, then let's start with the first concrete idea, which is dark radiation. Okay. So the motivation for dark radiation is mainly that it's a minimal extension. It's, I mean, the easiest model or mechanism I'm aware of how you can change lambda CDM at early times. I mean, there might be others, but this is a particularly simple one. And well, let's introduce a little bit of notation first in the case of lambda CDM. So if we talk about radiation in the case of lambda CDM, the background radiation, we can write it in the following way. We can say there is an effective number of relativistic degrees of freedom, bosonic relativistic degrees of freedom, which have an energy density that is pi squared divided by 30 times t to the 4. So that you have seen many times now, which scales like 1 over a to the 4. And this effective number of relativistic degrees of freedom, let's not write it in its entirety, is defined in the following way. It's all the bosonic degrees of freedom. So we are talking about fully relativistic degrees of freedom. So you count all the bosonic degrees of freedom. They are allowed to have different temperatures, so they don't need to be in thermal equilibrium. And T, by convention, T is the photon temperature. And then you count the fermionic degrees of freedom. They come with this factor 7 over 8, which accounts for the different spin statistics. So you count all of them. You also take their temperature divided by T, and you take it to the power of 4. And this is really how you can express the radiation density in terms of all the relativistic particles you have in your fluid, given that they are in thermal equilibrium, at least within subsectors. And then, in the case of lambda CDM, after electron-positron annihilation, we can calculate this G relativistic. And in that case, we get the following result. We get that we have 2 degrees of freedom corresponding to the 2 photon polarizations. So these are the photons. But there's an additional contribution from neutrinos. So you get this factor of 7 over 8. And what we introduce is an effective number of neutrinos. So we allow for in principle, for a different number of neutrinos. We could have more than 3. But in lambda CDM, this is going to be roughly 3. And we need to take into account that the neutrino temperature is not, at that point, is not equal the photon temperature. The reason is that neutrinos decouple from the fluid before this process happens. So in this process, the electrons, annihilate positrons and electrons and dump their entropy into the fluid, which raises the temperature, the photon temperature, relative to the neutrino temperature. So this is smaller than 1. And this is called the effective number of neutrinos. And for lambda CDM, it is 3.046. So you might wonder, why isn't it exactly 3? The reason is that when when neutrinos decouple, I mean, that doesn't happen instantaneously. And there is some overlap with the onset of this process. So there's some slight heating effect in the neutrinos too. And if you take that carefully into account, you get this small correction. But that's a detail. Okay. And now the idea is to look at lambda CDM plus dark radiation. And the idea is very simple. Just promote this parameter and effective to a free parameter. That's how people normally parameterize these models. So it's an effective parameterization. Where n effective goes to, taking this number, goes to n effective plus some delta n effective. So you have a change in that number. That doesn't mean that these degrees of freedom need to be neutrinos. It doesn't even mean that they need to be fermionic. It is just a way of parameterizing the existence of additional degrees of freedom. This is what the community chooses to do. Yeah. 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 Mm.
How would we interpret this additional effective? Is it interaction or is it like some other
new degree of freedom? I mean, I'm talking about the possibility that we have new degrees of freedom, which we understand, which we absorb into this n effective. This is the way it's typically done. Because all the bounds on dark radiation and so on are phrased in terms of delta n effective. So yeah. Yes, so what we do now in this case is we say there is an omega dark radiation, which is some number of relativistic degrees of freedom in the dark sector. So by dark sector, I mean that these degrees of freedom, we assume them to not interact with any degrees of freedom in the visible sector. So these are dark sector degrees of freedom, and we, for simplicity, we assume they are bosonic, and then their energy density is related to a dark sector temperature. So we introduce a dark sector temperature. Yeah. This is after they have annihilated. Yeah. So I didn't. So the result is this 3.36, and this applies after the annihilation. Before that annihilation, of course, that number changes. And if you go earlier in the history of the universe, this number gets higher and higher as all the massive particles of the standard model have been at some point relativistic and contributed to the radiation density. But this is the final value today after electron-positron annihilation.
There is dark radiation. Won't they also fall into these dark matter potentials or gravitational potentials?
Yeah, of course, they interfere with that. Yeah. Well, that depends on their perturbation sector and how we describe it. Okay, but let me start there. So we have a dark radiation fluid, a certain number of relativistic degrees of freedom in the dark sector with some temperature TD. And I also going to introduce this parameter psi, which is the relative difference between the temperatures between the dark and the visible sector, so T and TD. And then we can actually relate the dark sector temperature and this delta N effective, which are two ways of parametrizing this dark radiation. And what you find is that, so delta N effective, what we essentially do is we measure the dark radiation in units of the energy density carried by one neutrino. So one neutrino would be, so I mean, one neutrino species would be 7/4 pi squared over 30 times the neutrino temperature to the 4th power. And if I use these relations, we can derive that delta N effective is the number of relativistic degrees of freedom in the dark sector times 4/7 times 11/4 to the power 4/3. I'm going to explain where that comes from. Well, let's have a step in between, sorry. So it's the dark sector temperature divided by the neutrino temperature. And then we can use that the neutrino temperature is a little bit lower than the visible sector temperature and express it in terms of that. So what we find is that this is going to be 4/7 times 11/4, 11/3 times chi to the 4. Sorry, 4. And what we have used here is that the neutrino temperature over the visible sector temperature is 4/11 to the power 1/3. Okay, so we have a relation that relates this effective number of neutrinos, or the change in the effective number of neutrinos with the dark sector temperature and the number of new degrees of freedom in the dark sector. That's just the conventional way of parametrizing the presence of dark radiation degrees of freedom in the dark sector. Yeah. Yeah. So, okay, so why is that the right thing? Well, because N effective also counts the number of neutrinos. It's 3, right? So if we have the change in delta N effective, you have to compare it with 1 neutrino. Imagine dark radiation would be a 4th neutrino. Then what you want is that this goes from 3 to 4. So if this is 1 neutrino, then this would be 1, and indeed it would be increased by 1. So this is consistent. Now this 4/6 is something specific to neutrinos. I mean, our dark radiation degrees of freedom are completely decoupled. It's really just a way of parametrizing the existence of more degrees of freedom. So yeah. So this is independent from that. Yeah. Yeah. They are degenerate, as you say. So I'm just introducing this delta N effect. I could have done without it, but I'm introducing it because this is how in the literature people talk about dark radiation. This is how bounds on dark radiation and so on are typically stated. So that's why I wanted to work out how delta N effective relates to something more kind of understandable, just the number of additional degrees of freedom with a certain temperature in the dark sector. That's all. And once you can convert it into delta N effective, and then delta N effective just directly tells you what the total radiation density is, including the dark and the visible sector. That's all. I mean, it's really nothing mysterious going on. It's just two different parameterizations of the same thing. Okay. Then, so how does it look as an energy injection? So let's look at rho x, which in this case is rho dark radiation, divided by rho lambda CDM. So what we have is that at early times, it's a constant ratio because lambda CDM is radiation dominated, and this behaves like radiation. So if I plot that over the scale factor on a log-log plot, I'm just going to get a constant. But then at equality, we know that lambda CDM becomes matter dominated, so the energy density goes down like 1 over a cubed. So this ratio is, sorry, just a second. Yeah, it's going to go down like a to the minus 1, just because dark radiation scales, we assume massless particles. And then eventually during dark energy domination, it's going to go down like a to the minus 4. So this is this ratio. So this is a very broad energy injection. Okay. So this is the model that has been, I would say, most studied in the context of the Hubble tension as an early universe modification. But people early on realized that, I mean, there are certain problems with it, and they relate to the fact that it's so spread out, this energy injection. You see, I mean, early on, this is just a constant contribution to the energy budget. So there is a certain BBN bound. So BBN happens at a redshift of maybe 10 to the 9, so very early on. But as you see in this plot, dark radiation at early times doesn't go away. I mean, it just stays there. So you have to wonder about a bounce on additional degrees of freedom, relativistic degrees of freedom during BBN, because BBN sensitively depends on the expansion history. Because, I mean, during BBN, the light elements are formed, but the rates at which they are formed and when these processes freeze out sensitively depends on the Hubble parameter. So there's a bound from BBN, and it tells you that delta N effective is 0.11, sorry, minus plus minus 0.23. That's the latest bound I found from BBN on the number of additional relativistic degrees of freedom, non-interacting kind of in the dark sector. And it's typically, as I said, phrased in this language. And then you are going to show in one of the problems that this is not enough to resolve the tension. So in other words, this type of, if you respect that bound, the energy injection is too small, you lower the sound horizon too little. But there's, of course, an obvious way around, and that is to inject or to create that radiation after BBN. But that already requires new physics. And maybe at the very end on Friday, I can sketch a model which tries to achieve that through a phase transition, create this additional dark radiation in a first order phase transition. That's one possibility to get around the BBN bound. So then delta N effective is effectively zero around BBN and increases after BBN. But if you just take a simple dark radiation model, then you have to worry about that. Okay. And then, so yeah, there's also perturbations. And so let's ignore the BBN bound. So people typically looking at these models, they say, acknowledge that problem and say, okay, let's assume there is some mechanism that produces that radiation after BBN. And then you have two possibilities. The simplest one is free streaming. Radiation. So this means that the mean free path of the relativistic particles is larger than the Hubble scale throughout their evolution. Of course, at some point early on, you assumed them to be to be interacting to equilibrate, but that happens automatically if H becomes very well. Actually, also that depends, of course, on the details of your model. I mean, that is something you always need to consider in these models. I mean, how do you produce that radiation in the first place? But in the simplest scenario, you would say it's maybe produced during reheating. But then there's the possibility it's free streaming. But then there is the problem that free streaming leads to a phase shift in the CMB. And that effect is quite detrimental to the CMB fit. And what you find is that there is a bound from CMB on delta N effective that it N effective free streaming that it is minus 0.15 plus minus 0.21. So you see that CMB disfavors free streaming dark radiation. So I quote the most recent papers where I got these constraints from in these handwritten notes I put online. So this is one possibility, but there is another possibility of having a strongly interacting fluid. So the mean free path is much smaller than the Hubble length. And in that case, the radiation is not free streaming anymore. I mean, it doesn't move along geodesics. Instead, you can apply a fluid description. Fluid description is applicable. So then you can apply exactly the perturbation equations we looked at yesterday. And well, then if you study that, you find that the bound on delta N effective fluid is more favorable. So there, it slightly favors an N effective. Okay, but as it stands, these models, and when you play with that in the exercise, you will see also that number is not, so you see it goes from minus 0.15 to plus 0.15, but even that number is not quite enough to accommodate, to resolve the Hubble tension with that easy model. So what people nowadays study with dark radiation are more sophisticated models where dark radiation starts to interact, for example, with dark matter, or where you have mass thresholds. So what I assumed is that all these degrees of freedom are always relativistic, so they must have very small masses or are perfectly massless. But you can assume that they have masses that are not negligible and that they become non-relativistic at some point, and then you get these mass threshold effects when they annihilate, similar to positron-electron annihilation, and people also look into that. But maybe, because we have the next model I want to talk about is the early dark energy model. So, but I don't think there's enough time to start that. So let me maybe quickly summarize these mass threshold ideas, because they have become a little bit popular and they are interesting because they give a better, they are more efficient at addressing the Hubble tension because they can give you a more localized energy injection. So let me very quickly talk about mass threshold effects. So that happens. So in other words, what we look at is a change in the number of relativistic degrees of freedom in the dark sector, and that happens if particles decay or annihilate. Annihilation or decay when the particles become non-relativistic. And then we can use, and you have already heard about that, we can use entropy conservation to work out what happens. So the entropy density scales as the number of degrees of freedom times the temperature in the dark sector to the third power. That's how the entropy density behaves. That you get by looking at Bose-Einstein distribution of particles, and this allows you to derive this general relation for the entropy. But now the idea is that the entropy is conserved, but the absolute entropy. So what you get is that, so you need to multiply this by volume because it's a density. So we need to multiply it by the third power of the scale factor. And then you know that this quantity at some initial time, A equals A1, equals the same quantity at a later time. That's just entropy conservation. And then you can derive the change in the temperature or delta N effective by using that relation. So if we use our formula for delta N effective, we can derive that delta N effective at A2, so at the later time, divided by delta N effective at the earlier time. It's the ratio of these G's at the later and earlier time. Times the ratio of the dark sector temperatures to the power of 4. That's just using the formula I wrote down over there in terms of this psi. But then the visible sector temperature drops out because, and this can then be written as yeah, then I can use that relation to relate the temperatures in the dark sector at these two redshifts. And this is going to give me a factor of 4 over, a power of 4 over 3, because here the temperature comes to the third power. So overall, what you are going to find is, that so this is A2 and this is A1 to the power minus the third. So entropy conservation is going to tell you that the delta N effective, once you change the number of relativistic degrees of freedom in your fluid, is going to change in this particular way. And what you find is that it actually goes up if you reduce the number of degrees of freedom. So what you have, let me finish with that. Yeah, so you see it's a negative power here. So if the number of degrees of freedom goes down, so this is smaller than 1, then the overall ratio is larger than 1. So the delta N effective goes up. In other words, the dark radiation density goes up. So you start with a low value, and it suddenly jumps up to a higher value, and then it goes down again. This happens in these mass threshold models. So you realize something that is more localized. Okay. Yeah, let me stop here. Also there I have references if you're interested in these models, and they are more interesting than pure dark radiation models. I mean, there are the claims that they can reduce the Hubble tension to maybe the 3 sigma level roughly. Yeah, but let's stop here. Thank you.